Alright, welcome to another past paper question explained video. We are doing a paper from 2017 physics. Question 30 worth 4 marks. Now, the module that we're looking at is number 6, inquiry question 1. So for this module, like I said, we are looking at how charged particles behave in electric and magnetic fields. So think of this thought experiment. We have a proton, so that's a positive charge, that is traveling at a constant velocity, so it has a velocity going up that way, in a vacuum with no field present. Afterwards, we've included an electric field and a magnetic field at the same time. They are uniform in magnitude and direction. So the electric field is going in this direction. The magnetic field is also going in that direction. The velocity of the proton at the instant the fields turn on is perpendicular to the fields. Okay. So the question we have here, it says, analyze the motion of the proton after the fields have been turned on. So let's have a look at some of the things to look out for. So if we're looking at the motion, we can look at which direction the proton's moving. So if we look at the electric field always goes from positive to negative. Okay, so there's my electric field. There's my electric field there. So based on that idea, we know that the positive charge is going to be attracted to the negative plate. So the proton is going to get dragged towards this side in sort of a parabolic shape. It's going to be moving towards that direction. Okay, so that's proton essentially. The next part we're going to look at is obviously, actually, let's change that. So the proton, it has a constant velocity moving up. At this point in time, there is no initial velocity going in this direction. As soon as it's exposed to an electric field, it feels a force. So there's going to be some kind of acceleration going on there. So we know that the pathway of the proton is going to be parabolic, and it's also going to accelerate. So for the electric field, that is going to apply a force, okay, that accelerates the proton towards the negative plate in a parabolic shape or parabolic pathway. So that's what we would know from there. You could say the reason why it goes to the negative plate is because of electrostatic attraction. That's another little analysis you can do. The next bit we're going to cover is now the magnetic field. Now, magnetic fields or positive or charged particles in magnetic fields work slightly different from charged particles in electric fields. Firstly, let's try and work this out using the right-hand palm rule. So using the right-hand palm rule, we know that the positive charge direction is your thumb. The direction of your fingers is the magnetic field, and the perpendicular direction for the face of your palm is going to be the force. So if I look at this, the proton is moving up the page. So my thumb, if you try and imagine it with me, my thumb is going up the page as well. Okay? My fingers is going to line up with the direction of the magnetic field. The magnetic field is going to the left-hand side of the page. Okay, so what you should be able to imagine when you have your palm together, you should have a thumb pointing up, fingers pointing to the left, and the face of your palm should be pointing out towards you. So what we know is this proton, when exposed to this magnetic field, is going to push the proton out of the page. Okay, so for the magnetic field, using the right-hand palm rule as a guide, the proton will be pushed out of the page. But that's not it, okay? So it experiences the forces, or experience a force that pushes it out of the page, but we know if it is a charged particle in a magnetic field, it's going to do this sort of spiral clockwise motion. It's going to kind of rotate in circular motion, okay? So it's going to do that in a circular orbit. And you might think that's it, but there's actually one more thing. Remember, we are constantly changing the direction of the charged particle. So if we constantly change the direction, okay, so we are changing direction, we are effectively accelerating, the object. So if we're causing this incredible amount of acceleration, there is going to be some form of energy loss. Why? Because of a thing called electromagnetic radiation. So a simple electromagnetic radiation, or EMR. An example would be ultraviolet light, infrared light, all those kind of things. What we do know is, as long as you have a charged particle that is accelerating, okay, doesn't matter how it accelerates, but as long as it accelerates, there's going to be a generation of electromagnetic radiation. And this is just energy. So if we're creating all this energy from it spiraling into a circular shape, there has to be a way in which it binds by the law of conservation of energy. Okay, circular orbit. So this leads to a production of electromagnetic radiation. Okay, so according to the law of conservation of energy, that would mean that in order to produce this amount of electromagnetic radiation, the kinetic energy of this proton is going to decrease. And we know that kinetic energy, the formula for kinetic energy is half mv squared. So if kinetic energy is decreasing and the mass stays the same, that means the velocity will decrease as well. So we have lower kinetic energy, lower velocity, which means at the end of it, the radius of this magnetic field or of this circular path will also decrease as well. So therefore, radius of orbit, well, what we mean by decrease, we actually mean by increase. So the slower it goes, there's less force to pull it inwards, and so radius orbit will increase. Let me just check one thing. It's actually going to be a decrease. Do apologize there. So we're going to see a decrease in the radius. How come? If we actually look at the derived formula, R is equal to mv over qb. So when velocity decreases, okay, the radius is directly proportional to that decrease. So if velocity decreases, R decreases, hence we have a decrease in radius as well. So that's how you answer the question. If you want to go through other sources or other past paper questions, there are some links below and on screen. Make sure you read them if you need extra help.